This is probably my favorite optimization problem of all time. Now, you will definitely want to take notes on this because later on, you will get in a quiz in your future, you will get a problem very similar to this. And I will be asking specific questions. There's going to be one thing in here I'm going to do. I'm going to explain to you that you will not be responsible for. And when I give you a problem like this in a quiz, I will explicitly tell you the thing you're looking for is this, and I will give you a formula for it. But everything that we're about to talk about, you need to know. So this is an optimization problem. Given. We are going to take a sheet of paper or a sheet of cardboard. Cardboard. Let's do meters. It'd be nice to do this in meters. 2 meters by 4 meters. And what we're going to do is we're going to cut squares. Cut squares off the corners to make a box. Find the dimensions of the box to maximize the volume. Okay, so I'm reading this and see, okay, take a sheet of cardboard, blah, 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 cut squares off the corners and make a box, okay? Find the dimensions of the box which maximize the volume. I know from right there that we are talking about an optimization problem. And I know that there are 8 steps that we want to follow for a maximization, for an optimization problem. The first one is what?
Hold on.
Okay.
Okay, the first step.
Yep, first step that we were doing.
Draw a picture.
Draw a picture. Thank you. So, yes, draw a picture. So we're taking a sheet of cardboard 2 by 4. Okay, I'm going to go ahead and draw it like this. There's 4. There's 2. Doesn't really need to be there. Okay, so I'm going to go ahead and label this guy. Here's 4 right there. That's that entire length right there. 4. There. 2 is this entire length from there to there. At this point, I really don't have an idea of what this is even asking. Cut squares off the corners to make a box. But I think we've actually done something like this in class before. But anyway, at this point, I'm like, wait, what's going on? Okay, so now take a sheet of cardboard 2 by 4. Got it. Cut squares off the corners. Cut squares off the corners. Okay, so here's a corner, and we're going to cut a square off of it. So I guess that's what we're talking about. It has to be an equal length this way and an equal length that way. And so that's kind of what we're talking about here. If we're going to cut squares off the corners. Now, I didn't make this explicit. And if I were giving this to you as a quiz, I would have said cutting squares of equal squares off of each corner. That is, one of them's not going to be like 1 by 1.5 or 1. Well, I guess if they're squares, they have to be the same. One's not going to be 1 by 1 and the other one 0.5 and whatever, because as we're going to see in a minute, that wouldn't really make a box. Things wouldn't work out very well. And so, okay, cutting squares off the corners, yeah, to make a box. And what this means, and I think we've done this one before, is what we're doing then is this is going to be the base, whatever's left right here is going to be the base of the box right there. And so that, right, and here I'm imagining this is what will be left over, something like this. Boy, that's just terrible. Let's just draw the square. That's what's going to be left right there. And then it's going to have these little flaps. And those are the flaps that I'm going to use to, when I fold them up, what's going to happen is something like this. That flap gets folded up like this and makes that. That flap right there gets folded up like that to make that side of the box. This flap gets folded up this way like that. That flap gets folded up this way to make finally a box. So now I see what the thing is. Finally, after doing all this, I could get a picture of what's going on here. Okay. There's a couple ways we could do this, because I know step 2 is identify the quantity we want to optimize. But I'd kind of like to finish up my picture right now, because as of right now, since these are squares, we have one variable that's open. And in fact, it's the size of the square, right? And since it's a square, we don't need to worry about an X and a Y for the sides. I mean, the sides are exactly the same on the square. So what variable would you like to use for this?
Can we use X and Y?
We could use X and Y. Here's the thing though, because remember, the only thing that really is varying here, 4 isn't varying, 2 isn't varying. The only thing we need to know is what size of squares do I need to cut out, right? So in other words, we need to know basically what size, but since it's a square, right? Imagining here's the square I'm going to cut out. If I say that this width here is X, then, and if I say the height is Y, well, it's a square. It has to be equal. It's forced into being equal because it's a square. And that's the key right there, is to recognize like, oh, wait a minute. A square has to be equal size. So we really, at this point, we only need one variable. We call it X. And so if that length is X, then so is that length right there. So I say we use X. And what I'm going to do is I'm going to go ahead and in here, because I'm still kind of on step 1, I'm still drawing a picture. I'm kind of gone a little bit beyond, but I want to get my picture done before we move on to anything else. So right now, I'm going to say, okay, then this length from there to there is X. Right there. And of course, when I'm just to save space, like if I were being really meticulous, I would go in and put a little X here, 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 and here. But I kind of want this to look nice on the board. So I'm only going to do this once right here for all of these lengths, right? And we can see that all of that is X right there. I'm going to do that over here too. I'm going to say, okay, then that length right there is X, because that's the length of the square that I'm cutting off. And so that distance right there to there is X. And let's go ahead and label over here too. I'm going to say that that height right there from there to there is also X. So here we go. X from there to there. And X from there to there. Okay. Now, at this point, you might be tempted to just move on. And we can, and without there's more information that we could put on this picture. But if we felt, okay, we're good to go, we could move on, and we'll see that we'll need to update our picture a little bit. So either way we want to do it is fine. I'm going to go ahead and say, let's move to step 2, which is identify the quantity that we want to optimize. Buddy, that wasn't nice. What is the quantity that we're trying to optimize?
The max value.
The value of what? It says right on the board, maximize the what?
The value.
It's not what that says. It looks terrible, and I'll blame myself for that. But would that make sense? If I said maximize the value, you would have to say just.
I was really confused. Is that volume?
It's volume. Yeah. The volume.
Okay, I'm like he must be like going to explain that.
He'll come back to that. He'll come back to it eventually, because just like you're thinking, if I did say value, you would have to say the value of what, Justin? Of course, if you're maximizing something, it's the value, but of what? And so this is to maximize the volume.
That makes
of the box.
much more sense.
Okay, cool. So now we're on the same page. Okay, so let's do this again. Let's pretend that I wrote it well on the board and you could read it the first time. And I said, okay, we're at this point. And at this point, like I said, we could go and really get into this and get more information into our picture. But at this point, I'm not really sure what we're looking for. So let's go ahead and move to step 2. And if we need to come back to step 1, we will. Step 2, identify the quantity that we want to optimize. What is the quantity we want to optimize?
The volume.
The volume. And so that's the volume of this box. What is the volume of a box? Take all of this out of context and let's just pretend that we have this box right here. You would say I could calculate the volume by doing what?
Multiplying the length, the width, and the height.
The length, the width, and the height. Exactly. So we have the length, we have the width, we have the height. We take whatever the length is, we multiply by whatever that width is, and we multiply by whatever the height is. Okay, so now we've just done problem 3, right? We've written a function. That's a function. It tells you how to calculate a number, right? And the output of that function is the quantity that we want to optimize. So step 3 is done. Write a constraint equation. What now? Well, this is where we have to start using our brain. And we're going to say, wait a second here. And remember, the constraint is only to drop our multivariable function down to 1 variable. And right now we have 3 variables, right? There are 3 things that are varying: the length, the width, and the height. But maybe we need to come back to our picture, because remember, this length right here, whatever that is going to be that length right there. And so, and this is kind of what I'm thinking here. If we could write this, each one of these things in terms of x, right? Because that's our only variable up there. 4 isn't changing, 2 isn't changing. The only thing that we're allowed to change is x. So we should be able to get each one of these quantities in terms of x. And so then let's think about this. Here's the length. That length is that guy right there. In terms of x, what is this length? Let's think of how we would get it. We start off with this thing right here from there to there would be 4. Then what do we need to do? So think about this right here. This is how I like to do it. I imagine that I'm taking this, there's this line right here. It's that guy. And if I know that since that's the big picture, I'm starting off with that one sheet of cardboard. And I know from here to here, it's a total of 4 units long. And if I cut off that much there and that much there, how much am I cutting off right here? And how much am I cutting off right here?
Okay, so I'm sorry. I think I'm misunderstood. Are we trying to find the length of the shorter segment?
Yeah, we're trying to find the
okay.
base right here.
So that would be 4 minus 2x, wouldn't it?
Yes.
Okay.
So that is what I'm trying to find. Yeah. So I came back to say we need to find each one of these values here. And L was what I started off with. And I said L, that length of the bottom of the box, that's the bottom of the box right there. In fact, I could go ahead and say that this length right here is L, right? From there all the way to there. So now we're just saying, well, what is that? And you already did it, right? You said, well, and the way I think about it is if I start with 4 and I chop off X on one side and X off the other side, then what's left over from here to here is 4 minus X or 4 minus 2X, which is what you just said. So now, okay. That inner length is 4 minus 2x right there, which means that L, that length right there, I'm going to leave it as L equals 4 minus 2x. Okay, now what about this guy, the width? How long is that?
It's 2 minus 2x.
2 minus 2x. So I'm going to go ahead and label it right here, 2 minus 2x. And I'm going to write it right here, W equals 2 minus 2x. Finally, what is the height of that box?
Just x.
It's just x, because however much we cut off, right, that is how high those flaps are going to be. Each one of those flaps is x units long right there. And so the height must be x. So in this case, we didn't really have a constraint equation, right? And so if we're following along with our optimization process, we get to point 4, it says write a constraint equation. Well, that's kind of what we're doing. In this case, it's 3 constraint equations. One is that L equals that, and now L is constrained by that. W is that, so W is constrained by that. H is that, and so H is constrained. But now we could see that we're now in the position to go into step 5, where, and the whole reason that step 4 existed, right, was to get to step 5, which is to turn our function of, in this case, 3 variables down to a function of 1 variable. And so step 5, write this in terms of 1 variable. So V of X now, as I can see, that's my only variable, is equal to what?
4 minus 2x. Times 2 minus 2x.
And I'm going to use parentheses because those are my best friends here.
Mm-hmm.
And then finally times what?
X.
Times X. There we go. Okay, so now let's clear up some room because what we're about to do is going to get interesting. So the next step is to graph this function. And as of right now, we haven't talked about this. We will, like I said, after we do conic sections, then we're going to get into graphing general polynomials. It turns out that we could go multiply this guy out, which we're going to do in a minute. But first, to graph this, it's already factored. That means I know where the zeros are. That means I know where it goes through the x-axis. That's going to help me a lot. So I'm going to go ahead and do that right now. Let's clear off some room up here. So getting rid of this stuff, getting rid of the prompt. I'm first going to say, okay, let's copy this v of x down. I have the volume of this box as a function of x is equal to 4 minus 2x times 2 minus 2x times x. Now, since we're graphing, we are on step 6. Let's go ahead and find the zeros of this function. So you tell me, what are the zeros of this function? In other words, where is the output of this function equal to 0?
Would it be 2 and 1?
2, so you said 2. What I'm guessing you did is you said, well, this is a factored polynomial, and so it equals 0 whenever each one of these things equals 0. And so we could say, okay, so in other words, whenever 4 minus 2x is equal to 0, we get a 0, which I could solve by going, okay, 4 minus x, divide both sides by 2, and I get that x equals 2. And you would be right. You would say that when x equals 2, you get a 0. And over here, you say, okay, well, then when 2 minus 2x is equal to 0, that's the same thing as saying 2 equals 2x. So then when x equals 1, you get a 0.
Wait, couldn't it just also be 0?
And 0. Yes, absolutely. Because when you plug in a 0, you get another one. And now this also makes a lot of sense because I can see that this is going to be a cubic, right? Like we have 3 x's in there. And when I multiply everything out, we're going to have something times x cubed, something times x squared, and blah, 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 blah. And in general, those have 3 zeros. And so, okay, that feels good. We're going to learn how to graph this. Let me just kind of talk through it right now. Please, Peter, please don't. There we go. So I'm going to just graph right now. I'm going to draw my x-axis. My output is a v. And I could see that when I plug in a 0, or when I plug in a 1, or when I plug in a 2, my thing comes out to 0. And one of the things we're going to learn how to do is identify this is a cubic, which means that it's a positive, it's a negative cubic. Wait a minute. It's a positive cubic. And so it's going to come from up, go through, come down, go up, and then go back down like that. We will go into that in detail, but it's in general going to look like this. Okay. So this is when x is equal to 0. This is when x is equal to 1. This is when x is equal to 2. Now, one thing that we really want to do is identify a few things. This says that when x equals 0, my volume is equal to 0. What? Well, let's think about it. If x is equal to 0, did you cut anything off of the corners?
Yes. Wait, no.
No. I was about to just reach through and no, because no, if x is equal to 0, that means that you don't have a square. And so then what did you end up with? Well, here, let me get rid of this. So in the case where x is equal to 0, what you did is you said, okay, I have my box that's 4 by 2. I didn't cut anything off. And now, well, I don't have any flaps to fold up. And so my box is 4 by 2 by 0 because I can't fold anything up. And so the volume is 0. You have no volume at all. Now what happens when x is equal to 1? Well, let's think about this. It also says I get 0. Well, why would that be? Well, let's think about the length here. If we were to take 1 off of a corner, right? You can imagine that's a half, or like that's a quarter, that's a half. And if I make it all the way to 1, where I cut off a 1 by 1, okay? Well, when I do that over here at this corner, I also have a 1 by 1 that I've just cut off. And because that length is 2, if the side x is 1, well, then they exactly overlap, or they exactly meet right there. And so what have I done? Well, I've cut off a 1 by 1, but my length of this side was only 2. And so then the thing that I end up with, are you seeing what I'm doing here? Like, you see why you can't do this? If you've cut off a square of 1 by 1, you do that on the top, you do that at the bottom. The only thing that you have left is this piece right here. And you have no flaps left over. And you can kind of see that because if you plug that in right there, the width is now, well, it's 0. Right? There is no more width right there. Like, you've cut it off. You'd be left with 4 minus 1 minus 1. You would have 2 right here. This thing would be left over as 2, but now you don't have any flaps that way. In fact, you don't have any flaps at all. You have nothing. You've just cut that off, and you've cut that off, and now you can't fold anything up, and so you're left with a 1. Ditto if you did 2, but now this is where if x were equal to 2 and you had this and this, you've already hit a constraint, because if this is 4 and you're cutting off 2, well, it has to be 2 in this direction. And it has to be 2, but this is 2 right here, right? And so you've basically cut everything off. Like, you can't do that. You've run into problems. And in general, like, when you have a problem like this, you have to think about these limiting cases, right? So, like, for instance, if I'm just going to pick 2 numbers just out of the ether here, let's say it's 17 by 6. Okay, I could see that if I were cutting off corners here, we're going to run into a problem if my square is too big. Like, this square is fine right here. That's a perfectly good square because I'll have some left over. But if I make it bigger and bigger, eventually I'm going to run into a problem, because when there's going to come a time where they meet, and I could see that, well, if they meet, then I've just cut off an entire side. And as a matter of fact, I could see what length that has to be. If it's half of that length, so in other words, if it's 3 by 3 right there, then I will have entirely cut off a side. And now my whole setup of the problem doesn't even work anymore. And so you might look at this and say, well, the max volume that you could get, since this thing goes up forever, you could take like X equals 1,000,000. Well, no, you can't, because the problem only works in this scenario. And so there's only a certain range of numbers that actually work in here. It makes sense if X is strictly bigger than 0, because well, first off, if it's negative, then that just doesn't make sense. You can't have a negative length in this context. And if X is 1, that doesn't make any sense either, because like we said, then you've just cut off an entire side. Do you see that, what I'm saying with that? Why you can't have X equal to 1?
Yeah.
Okay, so now we could identify, and this is what's nice about graphing this thing, is we could identify that there is a specific range where this is going to work. And it's got to be between 0 and 1. My graph tells me that this works between 0 and 1. And then when I go back to check, I could see, like, yeah, actually that makes sense in the problem, that my actual answer has to be between 0 and 1. Because if I make X bigger than 1, well, or even equal to 1, then I'm just cutting off a side and I can no longer make a box. So it does not make sense. So, okay, all right, moving on. Let's see. We've used the constraint to turn the function of multiple variables down into a function of one variable. Check. We have 6 graphed the function. This is v of x that I've graphed. It looks like that. Sweet. Find the minimum and the maximum of the function, or find the minimum or the max. We know we're looking for a max. We know where we're looking for the max. We know it's between 0 and 1 because of the problem. And so you'd think, well, it's got to be this point right here. And you might think, oh, hey, this looks like a parabola. It's got to be halfway between there, right? Like the answer has to show up, since that's 1 and that's 0, it would have to be here at 1/2. And if this were a parabola, you would be right. But this is not a parabola. And these things don't behave like parabolas. And I'm pretty sure we could prove that it'll never occur halfway between. Uh-oh. What do we do? Well, this is like I said before, and so it's not here at 1/2. That is not the case. What we're going to do, in fact, I'm going to label this thing right here as x with a little m right there to be the max, the maximum value of x, which we don't know what it is. But once we know what it is, and one thing to notice is that we know it has to be between 0 and 1. So I'm going to go ahead and write that up there, that x max has to be strictly less than 1 and strictly bigger than 0. So that's the range that I'm looking for. And when I give you a problem like this, this is something I'm going to ask for. I'm going to say, find a suitable range. And what I'm asking for is, looking in the problem here, looking at the graph and looking at the problem, I could see that my max has to occur somewhere between 0 and 1. And so that's what I'm saying, that the max value of x, or the x for which we get a maximum volume, has to be between 0 and 1. So that's where I'm looking for my answer. Okay, so what do we do? Well, one option is to just graph this guy. And I'm going to do that here in a second. I'm going to plug them into Desmos, and we're going to see, we're just going to estimate what that thing should be. And then we're going to have some fun. Then we're going to learn a little calculus. So first, let's go ahead. Actually, let me prep this thing here. We're not going to do that yet. So, okay. This was, or actually, let me go ahead and share the screen as I do this. I wanted to hide something. That's why I got on there. So, okay. Here comes Desmos. Okay, can you see Desmos?
Yes.
Okay, so we are going to plug in the function v equals 4 minus 2x times 2 minus 2x times x. And hey, look at that. That looks very much like what I just did. And we could estimate, if we zoom in, I could see that there is a max value right here. And in fact, it even tells me what it is, right? That's nice. But if I wanted to, I could zoom in on it and estimate the x value where that occurs. And I'm going to estimate it's right around here somewhere. Sorry. Oops. So we're going to estimate it's right around here at 0. I'm looking down here. We're going to estimate that that's 0.423. That's what we're going to say, 0.423. Now I'm going to zoom back out to get the big picture here. Okay, so in fact, I'm going to write that on the board before we forget it. We are estimating that x max, x sub m, is approximately 0.423. So that's one way we could do it. And I'm going to stop the screen share for a second, and we're going to come back. But what we're going to learn is with calculus, there is a much easier, there is an exact way of finding this out. And it comes down to this. So first off, it's going to be a lot easier on us, believe it or not, if we multiply this bad boy out and get it into the standard form of a polynomial where we have some number times x cubed plus some number times x squared, etc. Why don't you go ahead and do that? Please multiply this entire thing out and tell me what you get. I'm going to do the same. So that's 4 minus 2x times 2 minus 2x. And then one more x. Let me know when you're done.
Okay.
Okay, what'd you get?
For, let's see, x. Hold on.
Okay.
Let me just check real quick.
Okay, cool.
Sleeping. Sleeping.
Who's sleeping?
Killer.
Kayla's not sleeping.
Okay.
Okay, what'd you get?
4x cubed
Yep.
minus 12x squared,
Yep.
8x.
That's what I got. exactly what I got. Okay, good. So, all right. So that was kind of preliminary for what we're about to do. Something to notice about mins and maxes and the slope of something. We've talked about this before, and this is what Calc 1 is all about. Is that if you have, let's use this right here. If we had the concept of a slope at a point, like up until now, we've thought about the slope as just the rise over run of a line. But what about if it's a curve, right? Well, we could define the concept of slope, and the way you do that, right? We've seen this before, is that we have a difference equation, right? Where we take v of x plus h minus v of x, and we divide by h, and that gives us the slope at any given point. So for instance, hold up, we're gonna get x max down here, 0.423. That was approximate. Okay, so and the idea is that what you're doing is you're taking your function v, and you want to know at some point x, what's its slope right here. And so what you do is you go some small distance beyond it. How far do you go? Well, a total of h. And you go to this point x plus h. And you plug that in. And you have then the rise is, well, you plug in x plus h and you get v of x plus h. You plug in x and you get v of x right there. So then your rise and your run are given by, well, the rise is just whatever the last point minus the first point is, which is v of x plus h minus v of x. Your run is x plus h minus x, or it's a total of h. And so then your rise over your run is this bad boy right here. And then what we do is we say, well, if we could let h get really, really, really small, then this slope that goes from here to here, as h gets really small, we're getting it closer and closer until when it gets to 0, then we have what we call a tangent line right there. And that is the idea, is that we have a way, and you've done this before, we've actually computed this with a few different functions, and we can find a new function. In fact, we call it v prime, but it gives you the slope. The output of the function is the slope at a given point. And so what we do is we say, okay, well, and we imagine here, like if you wanted to know the slope right here, it would be equal to, if you took a line and just touched it right there, it would be the slope of that line right there. And now here's the thing, here's the connection we want to make between this and optimization, is that if you had a function that does that, that tells you, okay, the slope over here is positive and it's not as positive, and the slope of this, look at that. Let's say there's a line that we're horizontal. What's the slope of that line right there? The slope of any horizontal line is what?
0.
0. Okay. And so, okay, that's what it would be right there. And we can imagine, okay, as we continue on, now the slope is negative and it's getting more negative, and it's negative here. And as we go along, it's still negative, but it's getting more positive. And finally, right here, what's its slope again?
0.
It's 0. Okay, and then we go on, and then it starts getting positive and positive, and it's positive. So interesting thing to know or to notice is that whenever you're at a max, the slope at the max is equal to 0. When you'll have a cracker in a minute. Whenever you're at a min, the slope at a min is equal to 0. So if we had a function which told us what the slope was at a given point, which is what that bad boy does, then we would expect it to look something like this. We'd say, well, we know that here at this point right here, the slope is equal to 0. We know here at this point, whatever that is, the slope is equal to 0. Here's another thing to notice is that between these 2 points, let's just imagine we have that we're drawing our slopes. We know that when we're right here, my slope is 0. And then when we move over into here, it's pointing down. So is the slope positive or negative in here? The slope of my pen, is it positive or negative?
Negative.
It's negative. And so, and we could see that that's the case this whole way. Like my slope is 0, okay? And then as we trace along this curve, the slope is negative, and it stays negative, stays negative, stays negative, stays negative until finally it hits 0. But we're in this middle area right here. We're saying that the slope, and I'm just going to write slope is negative. What about out here? Is the slope positive or negative or 0? Once we move past this, let's look at the pen. When we move out, then it starts to come up. Is that positive or negative?
Positive.
It's positive. The slope is positive. Slope is positive. And now what about down here before that original max? So we're back here before it. Is my slope positive or negative?
Positive.
Slope is positive. Okay, let's put this together. Slope is positive. So I imagine that if I had some kind of function that told me the slope of this thing, then it should be 0 right here. It should be 0 right here. It's going to be negative somewhere between here. And it's going to be positive over here. I don't know exactly what it looks like, but it should be positive like this, negative, and then jumps back up into positive. Like that's all we're saying right here. The slope is positive when you're over here. We're talking about the slope of my original function v. It's 0 right here. It's negative between here because it's coming down, right? So it should be a negative number. And then it comes back to 0 right here. That's what we're seeing. It's 0, goes to negative, comes back. And then the slope is positive, and it should stay positive forever because this thing goes on and on forever. It turns out that there is a very easy, and this is the part that you will not be responsible for. I'm not going to make you draw this either. I mean, you're going to have to graph this because that's what the whole section is going to be about. But this is when you go to take calculus, you're going to learn that that slope function that you're looking for, in other words, the slope of v, in fact, I'm going to write slope as a function of x, is equal to, and it has a colloquial name, or by convention, we call it v prime, whatever the original function is, the slope of it, we call it v prime, and we put a little prime right there. Turns out to be super easy to calculate. You just take whatever that number is and drop it down. What's 3 times 4?
12.
And what is 1 less than 3?
2.
2. Okay. Now you take that number, drop it down. What's negative 12 times 2?
24.
Negative 24. And what's 2 minus 1?
1.
1. Okay. What is now 8x? That x is to the first power. What's 1 times 8?
8.
And what is 1 minus 1?
0.
And what's x to the 0?
0. No. It's 1.
It's 1. Anything to the, even 0 raised to the 0 is 1. So 1. And so I'm not going to write it as x to the 0. I'm just going to write it as 1. It turns out, oh, buddy, you need a hug. You need a hug. Oh, come here. Thanks, buddy. Thank you. Thank you. Okay. So it turns out that this, and this is kind of interesting. Look at that. This thing, the slope function, the function that tells me the slope of the original thing at any given point, is a parabola. It's an upward facing parabola. And I'm willing to bet that its zeros are right here and right here. Let's graph it. Let's go on to Desmos and graph this bad boy. Okay, so here we go. I'm gonna graph this guy the way that we did it, and we could see it's the same thing, right? That the way that we wrote this guy originally with the, what is going on here? The green right there. That's how we wrote it originally. If I multiplied him out, we would end up with the exact same function right there. And so let's add on v prime. And it's funny, I could just write v prime and it'll do it, but let's call it the slope function. The slope of that is 12x squared. Oh man, it's not. It's reading this as, we'll just call it S for slope. Slope of x is 12x squared minus 24x plus 8. And look at that. It goes through here at 0. In other words, it tells me that the slope of the red function is 0 when the input value is 0.423. So in other words, going straight up, we should have a slope of 0 on the red function, and that's what we have. It tells me that when we're between these two places, so when we're over here somewhere, that the slope should be a negative number, and that's what we see. As we move past here, the slope is negative. That's what the purple function tells me. The slope has to be negative. And then it starts to get more and more positive until we end up right here at 1.5774. And there at 1.5774, the slope again is 0. And this is how you find the actual mins and maxes of these bad boys. And this is what you will be doing in calculus over and over and over again. But this is what we do. I'm going to stop sharing right now. Give me a second. And so the idea is this: we have something. It is no longer the case that the max occurs halfway between these points. It's now much more complicated. But it's not that bad. What we do is we say, well, we have a function which gives us the slope of the original function. We know that a max occurs where the slope is equal to 0. And so if this is the slope of the original function, we could say, where does this bad boy equal 0? And we do this. And we say, okay, we know how to solve this. We could say that occurs whenever x is equal to negative 24 over 2 times 12, plus or minus the square root. I'm going to cut to the chase here. I've already calculated this, but 24 squared, b squared minus 4ac. So that's 24 squared minus 4 times 12 times 8. This thing right here reduces to, well, first off, let's do this. Negative is 24 over 24. This is plus or minus, that's over 24. This thing reduces to 8 times root 3. 24 over 24 is 1. 8 and 24, those reduce because 24 is 8 times 3. And so we have 8 and root 3 like that. The 8s cancel and we get root 3 over 3. So that tells me that the slope of that, because remember, that's what we just did, the slope of the original function is equal to 0. The output of the slope function is 0 when x is equal to 1 plus or minus root 3. And oh, hey, look at that, right? So 1, you go to 1 plus root 3 over 3, 1 minus root 3 over 3, and it gives you exactly what we're looking for right there. The max occurs here. X max is equal to 1 minus square root of 3 over 3. This one right here, the min is equal to 1 plus square root of 3 over 3. But of course, that's, we know from our original problem, that's outside the bounds. That doesn't make any sense. We're looking for that guy right there. And I'm just going to double check and see what that gives me because I'm curious. I'm just going to plug this into Wolfram and go 1 minus square root of 3 divided by 3. And I get that is 0.4226, and that's actually where we got that. Remember, we rounded up from the 6 to get the 3. But anyway, here's the exact answer right there. Finally, we can take that to plug all that in because the answer was, or the question was, find the maximum volume. And what I could do is take that, and actually it might even be easier to just copy and paste this guy and plug him into there, into the original function. In fact, that's what I think I'm going to do. Let's do that real quick. Or maybe it asks for the dimensions. At any rate, yeah, we ought to get the dimensions too. So I'm going to do this real quick with that x. In fact, you could watch me do that. I'm going to do that right here. Okay, so there is 1 minus the square root of 3 over 3. That's where I got that it is equal to 0.4226, blah, 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 blah. I'm going to take that thing like this and find the length by going 4 minus 2 times that amount. 4 minus 2 times that. It says that that's equal to 3.154. So the length is equal to 3.1547. So let's round up to 155. Okay. The width was 2 minus 2 times that length, which is 1.155. 1.155. The height is x, which we know was equal to 0.4226. I can multiply all those guys together, and that will give you the exact same thing as just plugging it in. And since I have this, I'm going to copy and paste and just plug it in. So there's copied it. So 4 times that thing cubed, 4 times this thing cubed, minus 12 times that thing squared, plus 8 times the thing. Well, that's nice. I could check it. Yes, that is what I wanted. That's 4x cubed minus 12x squared, yes, plus 8 times x. That is the correct x that I wanted. It was 1 minus that is the one on the left. Should be good. And, oh, that's nice. 8 root 3 over 9 is that max volume right there. 8 root 3 over 9, which is approximately 1.5396, so 1.540. Okay. Okay, let's see. We drew a picture, we got this, we turned our 3-dimensional or 3-variable function down into a function of 1 variable, which we graphed, used our brains to say, wait a second, it has to be between 0 and 1, whatever that is. We don't know how to find that point. But, and this is what's going to happen in a quiz, I'm going to give you the means to find it, and you will be able to find where that slope is equal to 0. In other words, where the max is. Then, with knowing where the max occurs and having a nice picture drawn out, at least helps me a lot. I could say, well, that max value occurs right here, which is approximately this or whatever, which we could then plug into here to find out that my box is going to be 3.155 by 1.155 with a height of 0.4266, which if you multiply all those together gives you 8 root 3 over 9, or a maximum volume of 1.54 right there. Does that make any sense? Or was this just like way too much information in your face at once?
I don't think I would be able to do this in a homework assignment.
Okay. Yeah, no, this is hard. This is hard. It's very hard. Like this is a Calc 1 problem. Like, and by the time you do one of these, you will have done like 20 of this type of thing before you ever are just thrown out on your own. What you could definitely expect from me is that you construct a box, which I know was a homework thing before, that you get the box into this form and that you could graph that. The rest you will be guided through. And like I said, the reasoning behind where all this is, I don't expect it all. It's just, I want you to have seen this before going into calculus. Because I'm telling you, this is where people, even if they've been killing calculus all the way up to this, then it comes to the time to apply all of this stuff that they've just memorized by rote in their head, and they have no idea what to do with this. I want you to see it so that when you're doing it again, you might recall some stuff and it won't be so alien to you. And it'll also give you a motivation for, why the hell do we care about finding a slope function? Who cares? Well, it's kind of nice because even in an abstract sense, you could say, well, a maximum occurs where the slope is 0. And so if I have a function which tells me the slope, blah, 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 but that will start to piece together as you're learning that stuff. But hopefully, and my whole point for going down this with this long tirade is that it will be slightly less alien to you when you see it. So this will be coming sometime down the road, but I'm not, trust me, I will, if I choose to put this on a quiz, you will be walked through the hard stuff. I do expect that you could get to this point.
Yeah.
And by the time we're doing this, by the time I'm giving this to you as a problem, you will know how to graph this stuff. And that will be the main reason for it. And I probably won't even go through with this if the slope occurs, blah, 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 blah. It'll be more like, give me a range where I could expect a maximum. That is, I want to know it should be between 0 and 1.
Okay.
And you should be able to reason that through with everything that we've done before. So, okay. Are we good?
Yeah.
Well, Justin, kind of. I don't know. You tell me. Okay. So, so I do want you to see that this and this. Oh man, I really have to say this again. This type of thing that I did right here, where all I did was I looked at the original function and I was able to say, well, from here to here, the slope is positive. And all I did is I just took my pen and I just kind of traced it out and said, well, the slope is positive. There it's 0. There it's negative. There it's 0. There it's positive. And I was able to piece together what that slope function should just generally look like. This is so important to be able to do. And I find that very few people could do it. And so I wanted to show you what it looks like so that when in the future you see it again, it's not entirely alien. So I know it's entirely alien right now because it's the first time you've seen it, but when you first are exposed to this in a calculus class, you're just trying to keep up just in general. And then they throw something like this at you. Hopefully, just by having seen it before, you'll be that much ahead and you'll be expecting it. And when it occurs, it won't be so alien. This is very much what you do in first year calculus. Pretty much all you do in first year calculus is this stuff. So, okay. All right, so your quiz. Let's do it. So I'm gonna, get rid of all this stuff. This is, I believe, quiz 6. Yes, quiz 6. Take home. It is due Monday at 8. Monday at 8 a.m. Yeah, Monday at 8. That'll work. Chapter 8, section 2, page 349. Numbers 2, 4, 6, 8, 10. Chapter 9, section 6. Wait a second. Wait. Section 6, yes. Page 410 through 11. Numbers 12, 14, 16, 26, 28. And then chapter 9, section 8. That is on page 418. And this is the one I wanted to talk about. You're going to do only one, just number 6. There are parts A and B, which you will do, and then we're going to do one last thing. Well, it's like 3 last things. We are going to, so this is one of those where they give you 3 inputs and 3 outputs, right? Where they say in the first quarter, the company made $1,000. In the second quarter, the company made $2,000. In the third quarter, the company made $8,000. And then they give you exactly those points right there. They even write it out like that. And they say, using these data points, fit a parabola to it. right? So in other words, you're looking for a function, f of x equals ax squared plus bx plus c. And you know what to do with this. You plug in a 1, you get out 1,000. You plug in a 2, you get out 2,000. You plug in a 3, you get out 8,000. That turns into a system of equations, and you're going to use a matrix to solve for them. I did this one. It does not have crazy fractions in it. There are a few fractions. They are not crazy. They're pretty easy. And that whole right-hand column stays pretty cool the whole time. Pretty cool, but it's nowhere near as bad as that one that you did, which just blew me away and I gave you extra credit for because it was wicked hard. This is not that bad, but you will end up with this. And in part B, they ask you to predict what it's going to be in the fourth quarter. In other words, plug in a 4 and see what you get out. What you're going to do, the extra thing I want you to do is this. This gives you a function. I want you to determine if it has a min or a max. Of course, it's going to be a parabola. I just said that. You should be able to figure out if that parabola is shaped so that you get a max or if it's shaped so that you get a min. I want to know, which is it? 2. No max. No max. How did he know it was a min? That's crazy. Okay. We want to know where it occurs. And in this case, it's actually when it occurs, because I just told you they give you things for different quarters. In the first quarter, you made this, so that's a time. And so we're talking about when your input, but you know how I like to use the word where. We're talking about where on the x-axis, or where on the input axis does that occur. 3 will be what value? What is the output value? So when I'm asking where does it occur, I want to know what is the input value for that min or the max. What's the value? I'm asking for the output value of that. And the last little caveat I have here is I would like units on these, please. Like, this is a value of something. What is it in the context of the problem? Like if you just tell me 400 watts, apples, sandwiches, balloons, 400 watts. This is tricky. This one's tricky to tell me the value of it because it's in quarters. And what we have to imagine is, okay, after you've plotted your points, you knew you had 1 and 1,000. You knew you had 2 and 2,000 because that's what they gave you. And so if you found that the min or the max occurs, say, at 1.5, well, that would be, I guess, and this is the thing, this is the first quarter. The 1 occurs at the end of the first quarter. And so 1.5 would, I guess, be halfway between the first and the second quarter. Just as long as you're explicit about what the value means, because I'm asking for, give me the units on this. Like, I don't care how you say it, but tell me what it means. So for instance, if it were 1.5, we found that, say, there was a max at 1.5, I would say, well, it occurs halfway between the first and second quarter. Or you could say halfway into the second quarter. But that to me is like, hold up, does my teacher know what I mean? But if I say 0.5 of the way between the first and the second quarter, my teacher, no matter how stupid or ignorant he may be, will probably be able to get that. So I've talked already too much.